Hello everyone, November the 4th. All right, let's do this. Minimum number of changes to make binary string beautiful. You're given a zero-indexed binary string, have an even length. A string is beautiful if it's possible to partition it into one or more substring, such that each substring has an even length. Each substring contains only ones or only zeros. It can change any characters in S to 0 or 1. Return the minimum number of changes required to make the string S beautiful. So we have an even length string, and it's beautiful if it's possible to partition it into one or more substring, such that each one, so break down into small strings, and each one is even length, and each one must contain only ones or zeros. So in the first question, I have 1001. So if I change 1100, it can be seen that this is a beautiful. We can partition, make two changes. The second one we make one change, and the third one we make a zero change. Okay, seems to be a DP problem. Right, let's say we say DPI, okay, is the minimum changes to make S all the way to I plus 1 beautiful. Okay, so I have that. Now we want to try to see how do we get to DPI. So I have DP0. DP0, oh, 0 is not possible because it has to be even, right? So DP1. So what's DP1? Well, DP1 depends if the two are the same, that will be 0. If it's not the same, that will be 1. So in this case, DP1 is equal to 1. Actually, we can actually do this. Maybe help us. This is nothing. This is going to be 1. So DP2, right? So here. So I want to know. So previous is do one change, can make it this, right? Or even. So now I have, oh, all the odd position is not possible. So we don't consider the odd position. We only consider the even positions. Okay, so now I go here directly. So basically I say, okay, in here we need to change 1. Right? If we change 1, then it will work. And now you basically say, you look here. If these two are the same, then you copy this, right? If these two are not the same, right? If they're not the same, then you have to make a change, right? You have to make a change. If you don't make it, that's why this one will become 2. If you do not make a change, because it has to be even positions, because odd position really cannot do, right? So you go to even positions, and the previous even position, you know what's the minimum, okay? Now for this new position, because previously it's already all partitioned. So this, if they're not the same, then you have this sticking out. It really doesn't work, right? You cannot move it again to the previous. How do you move into the previous? It doesn't really work. So in this case, are we saying we just take 2, because the first 2 you have to make change, right? So you take 2, you make a change, and then you take 2. So you just take 2. And for every 2 you check, for every 2 you check. If the 2 are the same, you don't have to change. But if a pair, yeah, because eventually you get it down to even. So the smallest unit is 2, right? And it doesn't really matter. You get a smallest is 2, and if they're not the same, and you want to expand it, so I'm thinking like, is there a problem like this? You see these two, you want to change, but it won't because we start from these two. We won't start in the middle, right? We will not start in the middle. Like the one scenario that you will say, okay, it's not going to work. Like it has to have on both sides, otherwise it has to change, right? It has to has on both sides, otherwise this has to change. And if it has on both sides, it become an even, then we'll swap at the front. So I think this problem can be solved by simply by simply just two at a time, right? So we can say int, we can actually do int rest equal to 0, right? And then for int I equal to 1, I smaller than s dot length, I plus plus, if s dot char at I is not equal to s dot char at I minus 1, then rest plus plus, and then we'll return rest. Something like that. I'm not even sure if it's even. We'll run it. If it's not even, ooh, that's not right. Okay, so yeah, that is not right. I thought it will be sufficient. Why would it not be right? Because what we're saying is every time you see, like if it's the same, then you change, right? If it's not the same, because I can change, okay. So maybe that's the thing. You check the first two. Yeah, let's move this down a little bit more. I need a scenario where it doesn't work, so it can help me understand. Oh, invalid case because it's not even. Oh, plus equal 2. Ugh. Can I do this? Did it work? Oh, this one works. Yep. I was going to say, oh, how am I going to solve this? And then I realized I did it wrong. Yeah, because like my analysis, I don't feel anything wrong with my analysis. So it really troubles me that it doesn't work. So well, here's the idea. How do I explain it? So we go like 2, right? The if we go, yeah, we go from left to right. We go from left to right. The first two letters, yeah, have to be the same, right? And this, and if they are not, we must perform one change. There's no way around it, right? Now once they are settled, we need to move on to the next 2 letters, so on and so forth. Thus, the problem can be simplified as finding the number of pairs, right, in S that are not the same. basically, like, if you don't change, then you cannot make it work. There we go. That's the solution. Okay, let's read the solution. See anything when you can learn? Yeah, it is greedy. Whoa, hold a second. Loop through each character in the string while keeping track of the current sequence's length. If we reach the end of a sequence and its length is even, we can simply move on to the next sequence. If we find that the sequence has an odd length, we'll flip the last bit of that sequence to make it even. It's important to know that flipping the last bit will add an additional bit to the next sequence. So we need to account for this when calculating the length. I have no idea what it's talking about. What are you doing here? Current char, consecutive count, minimum changes required. Iterate through each character. So we do consecutive count, okay, when it's not the same. If the consecutive count is equal to 0, we have even count of characters. We can start a new sequence. Makes sense. If it's odd count, we need to change current character to change into the previous. Consecutive count set to 0, minimum change updated, and we update current char. I see what it's trying to do. So you go through this, right? You just do consecutive count, and if it's even, perfect. If it's odd, then the next one would change into even, right? Next one would change, and then you just move on. Proof. By flipping some bit other than the last bit. This one, all bits are the same, and let's start with a different bit. Two possible approaches. One is flipping the last one. Flip any other bit. Flip any other bit. One is split into two sequences of even length, but a non-terminal bit of length 1. More than one bit. Yeah. I think I probably hit the optimize. You just do 2, 2, 2, right? Yep. Okay. Yeah, this one is done. Alright, we're gonna move on to this one again. Okay, so we have some idea yesterday that does not work, which I think we can fix. So what we need to do is passing. We need to, did we submit it? Yeah, we submitted and it was wrong because we need to pass. We need to pass the, we need to pass the height into it, right? So after we get the heights, and you're passing the heights in. So at each one, you have the current height, and you have the left height, have the right height. So you know when you remove it. Wow, this actually make it much easier. I have no idea why I didn't thought about this. This is So we do get height, which is fine. And then after removal, so what we need is the node. We can have impact. We don't need this. We just need a. What do we need? Level. That's what we need. Right? We need a level. So the level plus your current height is, yeah. So find the height of the binary tree after the current node is removed. Okay, so if not impact, yes, and level plus 1, right, level plus 1. Otherwise, we get the left height and we get the right height, right, left height and a right height. Ooh, left height, right height, and I have a level. Right, I have a level. And then what we're gonna do is, yeah, I don't need any of this. So what we're gonna do is I have the left height, I have the right height. And if left height, if the two is the same, same thing, if is the same, then actually I'm at my current node, right? And what I need to know is, like, if I'm not impacting, then yes. But if I'm impacting, then we do the left, then we do the right. Okay? And if the left and the right is the same, then I still will get impacted. I have a level, right? I have a level. So I know how much I contribute. Oh yeah, I don't even need impact. I think if I have level and I get the left and right, then I know how much I contribute, right? And I'll compare, and then oh wait, hold on, I have the height, right? If I have the height, then that is going to be if I got removed, right? If I got removed, and if I'm impacting, yeah, I do think you still need impacting, right? If I got removed and I'm impacting, then the height is what I can contribute, right? The height is what I can contribute. So the level is what I can contribute. Wait, hold a second. If I got removed and I have level, if I got, so I'm here, I come here, level is 1, right? If I got removed, should be level minus 1 is what's remaining, right? What's remaining. So it does not matter in this case. All I shall do is, if not impacting is this, right? So now it's impacting. So we just say self.heights, no.val, try to go to maximum self.total height. Actually no, it's just your level. Oh, I still need the other side, right? Even if you're passing down, if you got removed, right? If you got removed and you have this much, right, is your contribution. So I basically I can get your contribution, but I don't know on the other side what is the second maximum, basically. Yeah, I don't know that. Oh, yeah, this is still not right. It's still not right. I have. Hey, how do I know the height after I remove a node? Now, after I remove a node, I remove myself. I know my contribution. So I need to know. In my subtree, it still doesn't work because I need to know. You always have to go back up, right? You always have to go back up. I don't want to go back up because I think the solution said you can just do top down once. You do it once and you can calculate. All right, I'm gonna give up on this one. Let's see. Left and a right traversal. Single traversal. Subtree size. Oh, what the hell is this? Eulerian tool. Holy crap. Jesus. Two largest cousins. My god. That is a lot of approaches. Okay. All right, let's reset our perspective. What's our solution initially? I forgot. Our solution initially was it was quite slow. It was I'll get the height and I'll have the left. Oh yeah, I remember. I get the left and right, and then I traverse back up. I remember this. I traverse back up, and it only passes after I turn everything into an array. Okay, let's read left and right traversal. Process each query separate by removing the specific. Track the tree's height as we traverse from the root. For any node, the height after removing its subtree is simply the height of the tree before reaching that node. This allows to avoid recalculating the height repeatedly. But you still, how do you know the height of the tree? We'll perform pre-order traversal, tracking the maximum distance from the root. However, if the maximum height is achieved in the right subtree, we may miss it when traversing the left. To address this, we perform a second traversal in reverse order. What the hell? We maintain array heights. During the first traversal, we update heights with the height of each node as it explores its left and right subtree. In the reverse traversal, we update heights if the current height is greater than the stored value. Wait, hold on. What? You do a traversal to get the heights. Isn't that deterministic? Traverse left to right. Current max height. Store the max height if this node were removed. Update the current max height. I have current height. And then traverse the left and traverse the right. I mean, this is not really height. This is from top down. This is the level, right? It's the level. I mean, technically it is the same. So it's kind of the height is reversed, right? So at this level, what is the maximum height? Okay, so we have a maximum height after removal. I just set it up, the current maximum height. And then I consider, because the current height, yeah. Which is like, I don't consider this, what is the current maximum height? Okay, if I don't consider this, what is the current maximum height? And then I move on. But this traversal give you weird result. Wait, what is the height determined? Is the height of the tree. Yeah, this is the height, right? But in this, well, I haven't finished reading it yet, but all right, I have to think about this. All right, I'll see you guys tomorrow. Adios.